What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, today we're going to take a look at eigenvectors and linear transformations. We're going to talk about our diagonal matrix representation. So I'll say suppose that A is equal to PDP inverse, where D is a diagonal n by n matrix. If beta is the basis for Rn formed from the columns of P, then D, diagonal matrix D, is the beta matrix for the transformation mapping x to Ax. Now, there's actually a clarification that I want to make here. We could say the same thing, really, about some non-diagonal matrix. So I could go here and I could make the following critique. I could say, suppose that A is equal to P times C times P inverse, where C is just an n by n matrix, not necessarily a diagonal matrix. Then we would still say that C, this matrix C, doesn't have to be diagonal anymore, that C is the beta matrix for the transformation mapping from x to Ax. And let's actually talk a bit about this further, and let's bring it back to a familiar discussion. Let's go ahead and let's say the following. Let's say let T be a linear transformation where T, what is it going to do? It's going to take a vector in vector space Rn and map it to another vector in vector space Rn. So it takes some input vector in Rn and maps it to some output vector in Rn. And just as we described this transformation back in section 1.8, we'll say that transformation T takes input vector x and maps this to A times x as the output vector. And what's nice about this is we can visualize a bit of what's happening. So let's say I have some set, and then I have some vector in that set in vector space Rn. Let me call that vector x, just vector x. And then I can map this to some output vector in vector space Rn. We'll call this A times x. And we can map this with transformation T. So say if I take input vector x and map to this output vector A times x, I can do that with transformation T. However, this is nice. We like this because it is in reference to a standard basis and a standard coordinate system. I don't have to describe these same things in a standard basis and a standard coordinate system. In fact, I could represent this same exact vector x, but I could represent it in a non-standard basis and in a non-standard coordinate system. So this could be x still represented, but now in terms of basis beta, so x sub beta, and it's still the same vector, right? I'm just not describing it in terms of a standard basis. I'm describing it in terms of a non-standard basis. And this will map me through some transformation to the same spot here, but instead of describing it in terms of a standard basis as Ax, this is going to be Ax in terms of a non-standard basis beta. And I'm still going to do this with transformation T. So these are really the same thing. We're saying instead of describing them in a standard basis or a standard coordinate system, I can describe the input vector and the output vector in a non-standard basis, in a non-standard coordinate system. Okay, but what if I wanted to work in this non-standard coordinate system? Is that something that I could do? And how does it relate to what we already know? Well, there are a few pieces that we're going to need in order to discuss this. Let's talk about what those pieces are. P is the change of coordinates matrix. And what this change of coordinates matrix is really good at doing, it's really good at taking something that is in a non-standard basis and putting it into the standard basis. So let's say I had vector x sub beta, and I didn't want this to be described in this non-standard coordinate system, in this non-standard basis. What I could do is I could multiply, so on the left side, by this matrix P, this change of coordinate matrix, and this is going to give me just classic vector x out. Right? This is going to bring me into the standard coordinate system, the standard basis. And similarly, if I think of this ax sub beta as sort of like it's one thing, think of it like it's just an output vector, so think of it like it's one thing. Let's say, okay, if ax is in terms of this non-standard coordinate system, so ax sub beta, if I multiply that by p on the left, my change coordinates matrix, that will bring me to classic ax. Now there's also matrix P inverse, and what P inverse does the opposite. So we'll say here P inverse does the opposite, where if I'm in the standard basis already, it'll bring me into that non-standard basis. So let's say I was in the standard basis, I had vector x, and I didn't want to be in the standard coordinate system. Well, I can get out of it if I multiply on the left side by P inverse, and that's going to bring me to vector x, but in this non-standard coordinate system, in this non-standard basis. And similarly, thinking of ax as if it's one thing, it's my output vector. If I don't want this to be in terms of the convenient, if I don't like the convenience and the luxury, this wonderful life of being in a standard coordinate system, if I don't want it anymore, I want to throw it all away and leave it behind, I'm going to multiply by P inverse on the left, and that's going to bring me to ax in a non-standard coordinate system, so ax sub beta. So, okay, so P is our change of coordinates matrix, really good at taking something in a non-standard basis and throwing it into the standard basis for us. Now, with these tools, we can start to sort of ask the following question. I have this really nice transformation T, and I already know back from previous sections very early in the course how it's going to behave in a standard coordinate system, where we know that T of x is described as matrix multiplication A times x. Well, what about transformation T when it's applied to something in the non-standard basis? So what about if I take transformation T and I'm going to apply it to vector x described in a non-standard basis, in a non-standard coordinate system? Now I know that this is going to give me out my output ax, but in that non-standard basis. But I want to know, how does this look in terms of the transformation? And we're going to be optimistic. We're going to hope for the best. We're saying our transformation T in the standard basis was just matrix multiplication. So I took my input vector, I multiplied it by a matrix, and that brought me to my output. What I'm hoping is that my transformation T applied on a vector in the non-standard coordinate system is going to be not dissimilar from this. That's going to be some matrix, call that matrix C for Corey, times this input vector, which is x in this coordinate system beta. So I'm hoping this is some matrix C times my input vector, and that this gives me my ax in that new coordinate system, that non-standard coordinate system. But I want to try to find some way to hopefully relate this back to what I'm already familiar with. If I can do that, then hey, I'm on top of the world. That's what I want to do. So let's see if we can explore this any further. And to be honest, there is already a relationship. It's already described up here. Spoiler alert, right? But let's see if we can corroborate this. So let's go ahead and focus on what we have. So it's C times x sub beta is equal to ax sub beta. But let's say that I didn't want ax to be in this non-standard coordinate system. I don't want it to be ax sub beta. Well, I could go here and say, okay, well, ax sub beta is really the same as p inverse times ax in the standard coordinate system. If I want to get out of the non-standard coordinate system, I can say, well, ax in terms of this non-standard coordinate system beta is p inverse times ax, where ax is in the standard basis. So that's p inverse times a times x. So we could say here, okay, c times x sub beta is equal to p inverse times a times x. And furthermore, I can keep working here. So I could say, okay, I'll leave this left-hand side alone for now. C times x sub beta is equal to p inverse times a times x. But if I don't want that x to stay in the standard coordinate system, well, I could say x is the same as my change of coordinates matrix p times x sub beta. So I could say, well, this is the same as p times x sub beta. And these two things are equal. And they have this matrix times a vector, right? So here I have matrix C, C for Corey, times a vector, this vector is x sub beta, equals p inverse times a times p times a vector x sub beta. Now, p inverse times a times p, think of this like it's one matrix. In fact, p inverse is a matrix, a is a matrix, p is a matrix, and if you multiply them together, matrix times matrix times matrix, this will give you some other matrix. So noticing that I have a matrix times a vector equals a matrix times a vector, noticing further that they're equal, and noticing that the vectors are identical. Matrix times a vector equals matrix times exactly the same vector, really leads us to the conclusion that these matrices should be the same, that C should be equal to P inverse times A times P. And this is the result that we were after. It's the result that I wanted to show. Now, it maybe doesn't look identical to what we said above, but it is an identical statement. So we were saying A equals PCP inverse, but if I solve this for C, then C is equal to P inverse times A times P. So there is a nice relationship between our transformation, our linear transformation, when working in the standard coordinate system and the standard basis, and how that transformation then is going to behave when I'm working in a non-standard coordinate system with a non-standard basis. And in fact, the relationship is right here, that C is equal to P inverse times A times P, or equivalently, A is equal to P times C times P inverse. Now, before we take a look at some examples, there's one more discussion I would like to have with you, and it's a bit more visual. I want to talk about how we can interpret this visually. So let's say I started with some vector x, and let's say I didn't have time to waste, I didn't want to mess around, and I needed to get to my output vector in a hurry, my output vector being a times x. I could do this very quickly just by multiplying by a. Multiplying by matrix A. However, if I got a full tank of gas and a lot of time to kill, I got some Gatorade, right? I got some Doritos, whatever I got, then I could take a bit of a more scenic route. And what I could do is I could go from vector x in a standard coordinate system, and I could map this to, it's really the same vector x, but now it's in a non-standard coordinate system, so x sub beta. And how would I do this? If I want to go from x to x sub beta in a non-standard coordinate system, I'd have to multiply by P inverse. But then from there, if I want to get to my output vector, but staying in that non-standard coordinate system, if I want to get to ax sub beta, I can just use my linear transformation, and I can multiply by matrix C, the beta matrix for the transformation. So multiply by matrix C, C for Corey. And then when everything's almost all said and done, when I want to return back to the standard coordinate system, so if I don't want ax in terms of basis beta, but I want classic ax, I can get there by multiplying by the change of coordinate matrix P. So here we'll say if I multiply by matrix P, that'll bring me to just regular ax. So I have some options here. how I want to travel. So take a look at what we have here. Students, we have a rectangle. So let's talk about it again very briefly. So if I want to go from x to ax, and I want to go from the standard coordinate system and stay in the standard coordinate system, and I don't have time to waste, multiply by a, that's going to bring me there. However, that's not the only way I can arrive at my destination. That is perhaps the nicest way to do it, but there's a really interesting way I can do it. I'd say a cooler way to do it if you want to do something cooler. Then what we could do is we could go from x to vector x in the non-standard basis, multiplying by p inverse to get there. And then if I want to go from input to output, I multiply by matrix C, my beta matrix for the transformation, to get to ax, but still in the non-standard basis beta. And then when I'm ready to go back to the standard basis, I would multiply by change of coordinates matrix P to go back to classic AX. So just an interesting way to sort of show how we can navigate around here. And just to reiterate, I don't have to be working with diagonal matrices. If I'm lucky enough to have matrix P formed from eigenvectors as column vectors, then matrix D is going to be a diagonal matrix where the diagonal entries of D are from eigenvalues. And we would say, well, okay, then D is this beta matrix for the transformation. However, I could talk about A equals P times C times P inverse, where C is any n by n matrix. It does not have to be diagonal, but we still consider C to be this beta matrix for the transformation from x to ax. Lots of really cool stuff here, very cool results. Let's talk about some problems here. Let set E, capital E, be the set containing e sub 1, e sub 2, and e sub 3, be the standard basis for R3. And you know how these vectors look, right? E sub 1 is the vector 1, 0, 0. E sub 2 is the vector 0, 1, 0. Little e sub 3 is the vector 0, 0, 1. So the standard basis for R3. Standard basis is very convenient. And let beta be the set of vectors b sub 1, b sub 2, b sub 3, be a basis for vector space capital V. And let T be a transformation that maps from R3 to vector space V, be some linear transformation with the property described here. Transformation T applied on x sub 1, x sub 2, and x sub 3 is equal to 2x sub 3 minus x sub 2 quantity times b sub 1 minus 2x sub 2 times b sub 2 plus, here in parentheses, x sub 1 plus 3x sub 3 times b sub 3. And I want to compute T of e sub 1, T of e sub 2, T of e sub 3, find all three of those in terms of basis beta, and then find the matrix for T relative to bases capital E and beta. And this isn't going to be as bad as it looks, but let's go here and let's talk about, we'll start at the very beginning, right? A very good place to start. T of e sub 1, think of this as the vector, and then x1, x2, and x3. So think about the vector x1, x2, x3. So with e sub 1, that means x1 is 1, x2 is 0, x3 is 0, is how we're describing this. So I can just follow here, and if it helps, you can make a little note. So for this one, we're saying x sub 1 is 1, but x sub 2 is 0, and x sub 3 is 0. And when I plug in, I'm going to get 2 times 0 minus 0 times b sub 1 minus 2 times 0 times b sub 2 plus, and it's this last term is the only one that mentions x sub 1, and that's going to be 1 plus 3 times 0 times b sub 3. So all of this is going to sort of simplify. I'm going to get 0 b sub 1 minus 0 b sub 2 plus, it's going to leave me with 1 b sub 3. We'll say, okay, well, that's b sub 3 then, is what I get. 1 b sub 3. And the rest are going to be very similar, right? T of e sub 2, well, this is going to be T of 0, 1, 0. So now x sub 1 is 0, x sub 3 is 0, but x sub 2 is 1. So if I go and I plug this into the relationship, I'm going to get 2 times 0 minus 1 times b sub 1 minus 2 times 1 times b sub 2 plus, and then it's going to be 0 plus 3 times 0 times b sub 3. Right, since x sub 1 and x sub 3 are the only terms there in that last piece. I got this, looks kind of crazy, so let's just Clean it up a bit. Looks better. Now if I go ahead and simplify here, what do I get? I get negative b sub 1 minus 2b sub 2 plus 0b sub 3. Or we could say as a final answer, we get negative b sub 1 minus 2b sub 2. And the third one, t of e sub 3, is going to be t applied on 0, 0, 1, where x sub 1 is 0, x sub 2 is 0, x sub 3 is 1. And if I plug into the relationship that I was given, that should be 2 times 1 minus 1. Sorry, 2 times 1 minus 0. I misspoke. 2 times 1 minus 0 times b sub 1. Because x sub 3 is 1. 2 times 1 minus 0, b sub 1. Minus 2 times 0, b sub 2. And then plus 0 plus 3 times 1, b sub 3. And we can clean this up, right? So I'm going to get 2b sub 1 minus 0b sub 2 plus 3b sub 3. Or if I'm looking for one nice final answer, we would say, well, this is 2b sub 1 plus 3b sub 3. So I have these results. But now it wants me to put this in terms of that basis beta. Right? And this should be, that basis beta should really be referencing b1, b2, b3. If I think about basis beta, right? It says right here, basis beta is b1, then b2, b3. So to put these in terms of that basis beta is just going to be a new representation of the work we've done. So t of e sub 1 in terms of basis beta, it's going to be a vector. But I can look here and I can say, well, what did I get for this first one? I got 1b3. In fact, if I look at my previous work, it's going to be even easier to see it. But it was 0b1, 0b2, 1b3. So this is the vector 0, 0, 1. If I want to put my transformation applied on E2 in terms of basis beta, similar idea, it's going to give me a vector. What did that give me for result? It gave me negative b1 minus 2b2, and then it was really 0b3. So it's going to be negative 1, negative 2, and then 0. And then one more of these to do. Transformation on e sub 3, but now in terms of basis beta, b1, b2, b3 in order in my vector. And that was 2b1 plus 3b3, really 2b1, 0b2, 3b3. So that should be the vector 2, 0, 3. So I can just assign these as vectors, is really what we're saying here. And then I want to find the matrix for transformation T relative to bases capital E and beta. Well, let's talk about how we can do that. And it's just gonna be organizing what we've done. So the matrix for transformation capital T relative to bases capital E and beta, how is it going to look? Well, let's talk about how it's going to look first. It's going to be a matrix, but it's going to take these vectors as column vectors. So it's going to be T at E sub 1 in terms of beta for the first column, T of E sub 2 in terms of basis beta for the second column, and then T of E sub 3 in terms of basis beta for the third column. And I actually have all of the pieces for it. So the matrix for T, I'm just going to use these vectors as column vectors. So my first column vector is 0, 0, 1. My second column vector is going to be negative 1, negative 2, 0. And my third column vector is going to be 2, 0, 3. And this is going to take something right from that standard basis and bring it into that new basis beta. So that's my matrix for T relative to the bases. Let's take a look at another example. Now we're talking about polynomial spaces again. So let T be a transformation that maps from polynomial space P2 to polynomial space P3. Remember, polynomial space P2 are polynomials of degree at most 2. Polynomial space P3 are polynomials of degree at most 3. And let this be the transformation that maps a polynomial little p at t into the polynomial t plus 3 times that polynomial little p at t. And the first question that I have is find the image of the specific polynomial 3 minus 2t plus t squared. We'll say, okay, so I can do this. So a transformation applied on some polynomial p at t is given by t plus 3 times that polynomial p at t. So the transformation applied on the polynomial 3 minus 2t plus t squared, all that my transformation is going to do is going to take that polynomial, but it's going to multiply it by t plus 3, is what it's saying. It says take your polynomial, multiply it by t plus 3, let me know what you get. So if I do this, I can go ahead and multiply this out, expanding this out. We'll, distribute. 3 times 3 gives me 9. 3 times negative 2t gives me negative 6t. 3 times t squared gives me 3t squared. If I'm multiplying the t in, I get 3 times t times 3 is 3t. T times negative 2t is negative 2t squared. And then t times t squared gives me t cubed. And then we'll collect like terms. So I have 9, my constant term. We want to write the constant term first, go in sort of increasing degree. Negative 6t plus 3t is negative 3t. 3t squared minus 2t squared gives me plus t squared. And then I have this plus t cubed. And this is the image. 9 minus 3t plus t squared plus t cubed. Next, I'm asked to show that t is a linear transformation. Now, if we remember the properties of a linear transformation, if I take two objects, u and v, the transformation of the sum of those objects is the sum of the transformations on those objects separately. And if I have a scalar, c times object u, vector u, is the same as the scalar times the transformation on that vector. Let's see if we can show it here in our polynomial space where we describe in the following. So let's say that we have two polynomials, call them p and q. The transformation applied on the sum p at t plus q at t, well, this would be t plus 3 is what we're going to multiply to that polynomial. And I like to start by thinking about this sum as one polynomial, just whatever p plus q is, right? I have a polynomial p, a polynomial q, add them together. However, when you think about adding polynomials together, you think a lot about precalculus, you think a lot about combining like terms and getting something that looks new. It doesn't look like just the two polynomials as add-ins. But imagine if we just took two polynomials and just put a plus sign in between them and didn't start combining like terms. That's really sort of the key to understanding what's really happening here. Because what I could do, if I really leave these as just separate polynomials but added together, combined via addition, think about distributing this. I'll say, well, if I distribute this, then I'm going to get t plus 3 times polynomial p at t, and then plus t plus 3 times polynomial q at t. And what is this by definition? Well, this is the transformation t applied on polynomial little p at t, plus the transformation capital T applied on polynomial little q at t. And that shows that first property. There's another property we got to show. Let's say we just have one polynomial little p at t, and we're going to scale it, c times little p at t. We're going to throw it in the transformation. So what does our transformation say? It says, whatever you give me, I'm going to multiply it by t plus 3. So t plus 3 times the polynomial c times p at t. And think of it this way. I have some polynomial, and then I'm going to multiply it by some scalar c. Typically what we would do is we would distribute that polynomial into all of the, we would distribute that scalar into all of the terms of the polynomial. What if we didn't do that? What if we just left it right in front and just kept the multiplication symbol? And that's really what's key here, because what I can do is I can leave this kind of factored out of the polynomial, and then I can actually bring it outside of the operation that's happening, right? I can actually say, well, what if I don't bring that through the polynomial? I can still multiply by it. Since everything is being multiplied here, I can take advantage of the fact that I can sort of shuffle these things around, right? I have these really nice properties with multiplication, right? Associativity, commutativity, we got it all. So I could say this is C times t plus 3 times p at t, and it's still the same result, but what is this by definition? This is scalar c times the transformation capital T applied on p at t. And that shows the two results to be a linear transformation. So yeah, we got it. Yeah, we got it. Now what's left? You better bring it. Find the matrix for t relative to bases 1t and t squared. This is the standard basis for polynomial space P2. Standard basis for polynomial space P2. And the other basis being 1t, t squared, t cubed. And this is the standard basis for polynomial space P3. So what this wants me to do is to start in the first basis and work with that. What I'm going to get out is in terms of this second basis. So you're looking at this, and maybe a common question is, well, how come it doesn't really feel like I'm doing much with this second basis? That's what we're going to get out. I'm going to work with this first basis, and the result of working with it from my transformation, I'm going to get something out that's in terms of this second basis. And I have to sort of work with it and interpret it, right? But let's work with that standard basis, 1t and t squared. These are the standard basis for polynomial space P2. I'm going to get something out that's in terms of polynomial space P3. Now, what does my transformation tell me to do? It says, well, let's start with one of them. Let's start with this first one, which is just the polynomial 1. Throw it into the transformation. My transformation says, whatever you give me, I'm going to multiply t plus 3 to it. T plus 3 times the polynomial 1 gives me t plus 3. We're going to go back to this in a bit because there's a better way to organize the information, but for now, I want this to just feel very organic and normal. Because next what I'm going to do is I'm going to take the next basis vector, which is just basis vector t, throw it into my transformation capital T. And that says whatever you give me, I'm going to multiply t plus 3 to it. And what's that going to give me? Well, it's going to give me t squared plus 3t. And then one more basis vector, t squared. Throw that into the transformation capital T. Well, that's going to multiply t plus 3 to it. What's that going to give me? Well, it's going to give me t cubed plus 3t squared. These are the outputs that I get. But it's going to be even better for us to assign them into vectors. Now, when I write these into vectors, notice my vectors go all the way up to degree 3. So this is in polynomial space P3 now. It's not staying in polynomial space P2 because I'm multiplying by something that kicks the degree up by 1. But what I want to do is I want to bring these in sort of a new nomenclature. I want to write them in terms of vectors. When I write these as vectors, it's very important to remember that it should go constant, coefficient on t squared, coefficient on t cubed, in that order. So my constant term here is actually 3. My coefficient on t is 1. And then it's a 0t squared and a 0t cubed because those terms are missing. When I go to build this next vector here, well, the constant term isn't there, so the constant term must be a 0, but then I have 3t, I have 1t squared, and then it must be a 0t cubed. And then this last vector here, t cubed plus 3t squared, no constant term, so 0, no t term, so 0t, but then I have 3t squared and 1t cubed. And this builds me my vectors, and from this I can get my matrix for t. So we'll say the matrix for t relative to bases 1t, t squared. This is the standard basis for polynomial space P2, and the basis 1t, t squared t cubed. This is the standard basis for polynomial space P3, and I didn't use this. I started with my input basis. I started with the basis in polynomial space P2. What I got, what it gave me, is something relative to this other basis. So now that's what I'm talking about now with these output vectors. That matrix for t, you got it. I'm just going to use these vectors as columns. So 3, 1, 0, 0 is my first column. My second column is 0, 3, 1, 0. And that last column, 0, 0, 3, 1. Now, since we were asked these questions in a very specific order, we did them in that order. But if I want to go back to, so this is my matrix for t, let me write that. If I want to go back to that first objective, I can use this matrix for t to produce that result. So that first thing said, well, find the image of 3 minus 2t plus t squared. So let me do this in a different color. 3 minus 2t plus t squared was my polynomial, little p at t. We could write this in as a vector. This is the vector constant is 3. It's negative 2 times t, and then it's 1t squared. And I can do this with matrix multiplication. So if I take my matrix for transformation t, which was 3, 1, 0, 0, 0, 3, 1, 0, 0, 0, 3, 1, and multiply to this vector, which represents my polynomial. So we can actually think of polynomial spaces like vector spaces. Remember, polynomial space Pn is isomorphic to vector space Rn plus 1. But then if I go ahead and do this, we can get the result this way. So we'll do the row vector rule. So here I'm going to get 3 times 3 is 9, and then 0 times negative 2, 0 times 1 gives me 9. Here I'm going to get 1 times 3 gives me 3. 3 times negative 2 gives me negative 6, and then 0 times 1, and I'll fix that up later. 0 times 3 is 0. We get 1 times negative 2 is negative 2, plus 3 times 1 is 3. And then last entry, 0 times 3 is 0. 0 times negative 2 is 0. 1 times 1 is 1. So this actually builds for us a vector. And that vector has entries 9, negative 3, positive 1, positive 1. However, this vector, we then want to interpret it as a polynomial in polynomial space P3. So we know constant first and then coefficients that follow. So that's 9 minus 3t plus 1t squared plus 1t cubed. Or just simply put 9 minus 3t plus t squared plus t cubed is what we're getting out. But is that not what we already got when we just dealt with it as polynomials? So it's just giving us a new way to organize and work with matrices. Very beautiful, though, very beautiful. Let's take a look at this next example. So here I'm mapping with some transformation t from polynomial space P2 into polynomial space P2, defined by t of a sub 0 plus a sub 1t plus a sub 2t squared is equal to 3 times a sub 0 plus 5a sub 0 minus 2a sub 1 times t plus 4a sub 1 plus a sub 2 times t squared. And assume that mapping is linear. Find the matrix representation of t relative to the basis beta 1t t squared. And this is the standard basis for polynomial space P2. And we're going to start with this. We're going to get something back out in terms of the same basis because we are mapping from P2 to P2. But let's see. So if I start with transformation t applied on polynomial 1, what does this mean? Well, if I really want to painstakingly write this out, I could say this is 1 plus 0t plus 0t squared is really what that polynomial looks like with all of its terms written out. It's just 1, but that means 0t, that implies 0t squared. And this is really trying to tell me a sub 0 is 1, a sub 1 is 0, and a sub 2 is 0. And then I can use this to figure out how this is going to map. So my transformation t applied on 1, I'm going to get 3 times 1 plus 5 times 1 minus 2 times 0 times t, plus 4 times 0 plus 0 times t squared. So how's it going to look when everything's all said and done? I'm going to get 3 plus 5t plus 0t squared. Or we could just simply write this as 3 plus 5t. What about the transformation applied on t? Just a standard basis vector t. Well, keep in mind what this means. This means a sub 0 must be 0. A sub 1, the coefficient on t is 1. And that a sub 2 is 0. Drop my pen. So let's see, how is this going to look? Well, okay, so I'm going to get 3 times a sub 0, so that's 3 times 0, plus 5 times 0 minus 2 times 1 times t, plus 4 times 1 plus 0 times t squared. Or then this is going to give me 0 plus negative 2 times t plus 4 times t squared. Or if I want to just write this out a bit more succinctly, we could say negative 2t. Clean that up. You're worth it. Negative 2t plus 4t squared. We got one more to go, right? T applied on basis vector t squared. And this means a sub 0 is 0, a sub 1 is 0, but a sub 2, my coefficient on t squared is 1. Right? It's described right here as well, right? T squared means a sub 2 is 1, but all these other a values are 0. So it's going to give me 3 times 0 plus 5 times 0 minus 2 times 0 times t, plus 4 times 0 plus 1 times t squared. There we have that. 4 times 0 plus 1 times t squared. And when I go and clean this all up, it's going to give me 0 plus 0t plus 1t squared. Or we would probably want to just write this very cleanly as t squared. But to build this into a matrix really means that we want to be building these outputs as vectors. So if I go back to this first one that I found, if I haven't done it yet, I can do it now, that I can represent this as a vector in polynomial space P2, so it's going to have 3 entries. 3 plus 5t plus 0t squared should be 3 for the constant, 5 for the coefficient on t, 0 for the coefficient on t squared. This next vector representing negative 2t plus 4t squared, well, 0 for the constant, negative 2 for the coefficient on t, and 4 for the coefficient on t squared. And then lastly, this vector that represents t squared, 0 for the constant, 0t, 1t squared. And we can say the matrix for transformation t, I can build this matrix just taking these vectors to be columns. My first column should be 3, 5, 0. My second column should be 0, negative 2, 4. And my third column should be 0, 0, 1. And this is going to be my matrix for the transformation as described. So I have this really nice matrix representation relative to my basis. I have this extra space left over. What do you think? Is this fun? Let me know. I like these problems. I think they're very interesting to think about. But I like this section. Let's take a look at this next question. We'll go back to the yellow. Define the transformation t, which takes a polynomial in polynomial space P3 and maps it to a vector in R4 by the following. This is a really cool description. It says transformation applied on polynomial P is going to spit out a vector with evaluations of that polynomial. The first entry is P evaluated at negative 2. The second entry is P evaluated at 3. The third entry is P evaluated at 1. and the fourth entry is p evaluated at 0. So essentially, we're given a polynomial of degree at most 3, and we're going to fill in these 4 entries to a vector just based on what we get when we plug numbers into the polynomial. Plug -2 in, plug 3 in for the variable, plug 1 in, plug 0 in. And that's how we're going to build these vectors. I want to start by showing that t is a linear transformation. So let's say, what if I had 2 polynomials, t of little p plus q? Well, think of p plus q as one polynomial, and I would take that one polynomial and I would evaluate it at -2. I would evaluate it at 3. I would evaluate it at 1, and I would evaluate that polynomial at 0 to get the different values for my vector. But like we were saying earlier, if I don't start combining like terms and mixing and matching everything, and I sort of leave it as 2 separate polynomials, then really what I can do is I can take all of the terms of p evaluated and bring them to the front, and then all the terms of q evaluated, sort of keep them to the other side, and really keep them sort of separated that way. And I can really view this then as p at -2 plus q at -2 is really the same thing. And then p evaluated at 3 plus q evaluated at 3. And p evaluated at 1 plus q evaluated at 1. P evaluated at 0 plus q evaluated at 0. And right here, I can split this up using properties of vectors into the sum of 2 vectors. I can say, well, this first vector, all the p's, p of -2, p of 3, p of 1, p of 0. And this second vector here, all the q's, q of -2, q of 3, q of 1, q of 0. And that by definition, this is my transformation t applied on polynomial p plus my transformation t applied on polynomial q. So we can show that first property for linearity. What if I have a coefficient, though? So let's say transformation applied on some scalar c times polynomial p. Well, think of c times p as the polynomial. So how am I going to build this vector? Well, it's going to be polynomial cp evaluated at -2, polynomial cp evaluated at 3, polynomial cp evaluated at 1, and polynomial cp evaluated at 0. But if I'm not, distributing that scalar in and leaving it sort of factored out, then I can actually bring it, if I end up plugging in values for all of my variables, plugging into my input, I can still bring that scalar all the way out. And I can think of this as c times polynomial p evaluated at -2, c times p evaluated at 3, c times polynomial p evaluated at 1, c times polynomial p evaluated at 0. And now I can bring this scalar c outside of the vector and say, well, this is just c times the vector with polynomial p evaluated at -2, polynomial p evaluated at 3, polynomial p evaluated at 1, polynomial p evaluated at 0. And by definition, this is c times my transformation t applied on polynomial p. So I have that second property for linearity. Second property. Let's get the purple. I'll sort of, because things got a little messy here, but this separates those 2 properties. And what do we want to do next? So we showed the transformation is linear. Now I want to find the matrix for transformation t relative to the basis 1t, t squared, t cubed for polynomial space P3, and the standard basis for R4. So I'm going to start with working with the standard basis for polynomial space P3. And what I'm going to get out is going to hopefully be in terms of the standard basis for R4. And my transformation, just to remind, takes a polynomial p and spits out a vector in R4. It's going to be p evaluated at -2, p evaluated at 3, p evaluated at 1, p evaluated at 0. We're just plugging into polynomials. So if I start with the basis vector 1, think of the polynomial 1. You have the polynomial, f equals 1, if that's familiar from calc, pre-calc. If I have the polynomial 1, and I'm supposed to plug -2 into it, well, there's nowhere to plug in. It's just going to give me 1 back out. Similarly, if I try to plug 3 into it, there's nowhere to plug it in. It's going to give me 1 back out. It's a constant polynomial. Plugging in 1, well, anyways, it's 1 already, so already ahead of the game. You can't plug 0 in either. There's nowhere to plug it in. It's just always going to spit out the constant value. A constant valued polynomial. There's nowhere to plug in. It's already set in its ways. But that's different than if I have the polynomial t. We think of this sort of like the identity function, right? So if I'm plugging in for t and my polynomial is polynomial t, if I plug -2 in, it's just going to spit -2 back out. If I plug 3 in, it's going to spit 3 back out. If I plug 1 into the polynomial t, it's going to spit 1 back out. And if I plug 0 in, it's going to spit 0 back out. Well, what about if I plug in t squared? Well, t squared is my basis vector, right? So if I'm plugging into t squared, if I plug -2 into t squared, it's going to square it. It's going to give me 4. If I plug 3 into t squared, it's going to square it. It's going to give me 9. If I plug 1 into t squared, it's going to give me 1 times 1 is 1. If I plug 0 into t squared, it's going to give me 0 back out. And almost done. My transformation capital T applied on basis vector t cubed. If I plug -2 in to t cubed, it's going to give me -2 times -2 times -2, which is going to give me -8. If I plug 3 into t cubed, it's going to give me 3 times 3 times 3 is going to give me 27. If I plug 1 into t cubed, 1 times 1 times 1 gives me 1. And if I plug 0 into t cubed, 0 times 0 times 0 gives me 0. Now I have all these vectors, and we want to build that matrix for transformation t. So the matrix for transformation t relative to the basis 1t, t squared, t cubed, the standard basis for polynomial space P3, and the standard basis in R4, which we could say is E1, E2, E3, E4. I'm going to get this transformation matrix for T. So it's a matrix for T is equal to. I just want to take these vectors and use them as column vectors. So the first column is 1, 1, 1, 1. Second column was -2, 3, 1, 0. Next column was 4, 9, 1, 0. And this last column was -8, 27, 1, 0. So we just take these vectors, throw them in as the column vectors in order. And I could use this to answer further questions. If I want to use matrix multiplication, if I want to think about this just in terms of our course material, I can now do that. Let's take a look at this next question. Just a little bit left to go. Thanks for sticking with me. Hey, if you're still watching the video, let me know in the comment section below that you're still watching the video. I want to find the beta matrix for the transformation x to ax, where beta is the set made up of vectors b1 and b2. Now, we talked about this at the very beginning. Let's see what we said all the way. A is equal to PCP inverse. C is an n by n matrix, and the matrix C is the beta matrix for the transformation x to ax. We actually solved for C directly too. We said C is P inverse times A times P. So with that in mind, keep going. Keep going. We had fun. It was good. We liked. Keep going. C is equal to P inverse times A times P, and C is the beta matrix for the transformation x mapped to ax. Now, I really have almost all of the pieces. So here, this set beta that I have, the set beta is going to be how I build matrix P. Let's go back. If beta is the basis for Rn formed from the columns of P, so if I'm building matrix P, I'm using the basis beta to build those columns. Keep that in mind. So we'll say, okay, so I can actually find all of these pieces. Given matrix A, we're looking right at it. Matrix P, the so-called change of coordinates matrix, is going to have vectors b1 and b2 as columns. So matrix P has column -1, 2, and then -1, 1. I can now continue to find P inverse. P's inverse. 1 over the determinant. -1 times 1 gives me -1, minus -1 times 2 gives me -2. And here I'm going to multiply into this. The entries on the main diagonal, I want to exchange them. So 1 and then -1. The entries off the main diagonal, I want to flip their sign. So where -1 is, now it's +1. Where +2 is, it's now -2. And what is this? What is this term that I'm scaling by? 1 over -1 plus 2? Well, that's just 1. So 1 over 1. So really for P inverse, I just get this matrix. But then C is equal to P inverse times A times P. So I just have to do the multiplication to find this beta matrix. So C is equal to P inverse, I write that first, times matrix A, times matrix P. Let me just write matrix P while I'm here, because I got to scroll up to see matrix A, because I haven't used that yet. Matrix A has entries row-wise, -4, -1, 6, 1. And now I can go ahead and multiply. Remember, I have to go from left to right. So I'm going to start here multiplying these two together. Row, column rule. 1 times -4 plus 1 times 6 gives me 2. 1 times -1 plus 1 times 1 gives me 0. Second row, back to the first column. -2 times -4 plus -1 times 6. So that gives me 8 minus 6 gives me 2. And then second row, second column, -2 times -1 plus -1 times 1. That gives me 2 minus 1 gives me 1. But I still have to multiply here by matrix P. Be the last step left. And that's going to give me matrix C. So we'll do row column rule again. 2 times -1 plus 0 times 2 gives me -2. First row, second column, 2 times -1 plus 0 times 1 gives me -2. We'll go down to the second row, but back to the first column. 2 times -1 plus 1 times 2 gives me -2 plus 2 gives me 0. And second row, second column, 2 times -1 plus 1 times 1, -2 plus 1 gives me -1. So this is my beta matrix for the transformation. So matrix C is the so-called beta matrix for the transformation. We computed it, we found it by doing P inverse times A times P. So we have our beta matrix for the transformation from X to AX. A blank page here, so we just write a little note, having a nice time. Smiley face. And just a little bit left to go. So here I want to define, this will be our last question, define the linear transformation T mapping from vector space R2 to vector space R2 by T of X equals A times X. Find a basis beta for R2 with the property that transformation T sub beta is diagonal. So this is a sort of a new notation, but this is saying find a basis beta for R2 with the property that the beta matrix for the transformation is diagonal, some diagonal matrix, capital D. So assuming it's a matrix, right? So this is really asking me to interpret diagonalization, which we talked about in the previous section. So this really ties together the two sections very nicely. I'm given this matrix A with rows 1, 2, 3, negative 4. Let's find A minus lambda I, because I'm going to have to diagonalize. So subtracting lambda from the entries on the main diagonal. And then I want to find the determinant of this matrix. So that's going to be 1 minus lambda times negative 4 minus lambda, and then minus 2 times 3, which is 6, equals 0. Expand this out. Negative lambda times negative lambda is positive lambda squared. I'm going to get 4 lambda minus lambda gives me plus 3 lambda when I combine those like terms. Negative 4 minus 6 gives me negative 10 equals 0. And if I can factor this, I want to factor it. Looks like it'll factor nicely. Multiplying to negative 10, but adding to 3 should be lambda plus 5, lambda minus 2, which is going to give me my eigenvalues. Let me write them over here to the left. Lambda equals positive 2, lambda equals negative 5. 2, negative 5 for the eigenvalues. Now I have to build my eigenvectors. So let's start with lambda equals 2. And I'm going to plug into A minus lambda I. I'm going to augment with the 0 vector. So if I subtract 2 on the main diagonal, 1 minus 2, or I can look here, 1 minus 2 gives me negative 1. And then 2, and then augmented with 0. And then I'm going to have 3. And negative 4 minus 2 is going to give me negative 6, and then augmented with 0. Now, I can go ahead and scale. So here I can do negative row 1, and I can do 1/3 row 2. So if I flip the sign on row 1, I get 1, negative 2 augmented with 0. If I divide everything in row 2 by 3, I get 1, negative 2 augmented with 0. And these rows are identical, so I can eliminate row 2, replacing with row 2 minus row 1. Gives me my row of all zeros. And I can work with row 1 to build my eigenvector. So that's saying, okay, v1 minus 2v2 equals 0, or v1 equals 2v2. So building this vector, I'll say, well, let the second entry v2 be 1. The first entry v1 is 2 times 1, gives me 2. So this is my vector, and this is my vector associated with eigenvalue 2. Now I want to do the same work, but with the eigenvalue negative 5. So I'll say, well, what about when lambda equals negative 5? Plug into A minus lambda I, augment with the 0 vector. So here I'm going to get 1 minus negative 5, so that's 1 plus 5 gives me 6. And then 2 augmented with 0. And then I'm going to have 3. And negative 4 minus negative 5, that's negative 4 plus 5 gives me 1. And here we can see if I scale row 1, we'll do 1/2 row 1. It's going to give me 3, 1 augmented with 0. Row 2 is identical. So then I can eliminate row 2, replacing with row 2 minus row 1. Gives me a row of all zeros at the bottom. And my row 1 is 3, 1 augmented with 0. Let's build a vector from this. So we have 3 times v1 plus v2 equals 0. If I solve for v2, we'll say v2 is equal to negative 3 times v1. And I can build a vector from this. I'm going to pick v1, my first entry, to be positive 1. And then v2 is negative 3 times that. So negative 3 times 1 gives me negative 3. And this is my vector associated with lambda equals negative 5. Now, from here, if I was looking to diagonalize, I can state what those matrices are. So we could say matrix P and diagonal matrix D. Working in R2, I already have a good idea as to how half of the entries of my diagonal matrix are going to look. The diagonal entries, the entries on the diagonal, are going to come from the eigenvalues. And I choose to just go in order. My eigenvalues were 2 and -5. So you could flip them, but I'm not going to because I'm not so creative. But what's important is that the columns of P are respective to this. So the first column of D has for its diagonal entry eigenvalue 2. That eigenvector in column 1 should be 2's eigenvector, which was 2, 1. And then with eigenvalue -5, that should be in the second column, that corresponds to the eigenvector 1, -3. Now this is diagonalization. We've done this already. This isn't really answering the question. The question says, find a basis for a set beta in vector space R2 with the property that the beta matrix for the transformation is diagonal. Now, my matrix D is diagonal. My basis for beta should be coming from the columns of matrix P, like we described earlier. So if I'm looking for that basis for beta, that should be coming from the columns of matrix P. So we can actually state what that basis is. So if I'm looking at that matrix P, that's going to build my basis. So my basis for beta, my set beta, is going to be the set of 2 vectors. It's going to be those eigenvectors, right? So the vector 2, 1 and the vector 1, -3. And this is going to build my basis for beta. And this is with the property that T sub beta is diagonal. This diagonal matrix is my beta matrix for the transformation. Hey, hope you had a good time. Was one of my favorite lectures, definitely. I hope you enjoyed this one. No matter where you are and what you're doing, remember to always keep learning, keep dreaming, and follow your heart. I'll see you next time. We'll be back at it with more math, more cats, more fun stuff. Not really going anywhere. Just click on the next lecture video. We'll be back in it to win it. All right. Until next time, I will see you later. Take care of yourself.